When you build with RAG, it works really well up to a point. Not because retrieval is bad, but because retrieval on its own can only go so far. If an AI application can answer questions but struggles to decide what to do next, this video will help explain why. RAG is often described as a way to make language models smarter by giving them access to external knowledge. But what it really does is much more specific than that. RAG makes a system better informed. It does not make it better at deciding or acting. The basic flow is simple. A request comes in, relevant text is retrieved from the documents or databases, that context is passed to the model. The model generates a response, and then the system stops. Each interaction is treated as a standalone event. For tasks where the job ends with an answer, this is perfect. Internal documentation, policy questions, summaries, reports, anywhere the information already exists and the output is text, RAG is exactly the right tool. In that sense, RAG is very good at reading. The problem starts when reading is no longer enough. Consider a system designed to handle production alerts. An alert fires, the system retrieves runbooks, past incident notes, and configuration details using RAG. The model correctly explains what the alert means and even suggests a likely fix. Everything looks right, but nothing actually happens. The configuration isn't updated, the alerts keep firing, the system doesn't know whether the suggestion worked because it never tried. Someone has to step in, interpret the answer, execute the fix, and verify the result. The retrieval worked, the answer was correct, the system still failed. This is the moment where RAG reaches its architectural limit. The issue isn't missing data, it's missing control flow. RAG has no built-in concept of progress, state, or outcome. It cannot decide what to do after generating a response, and it cannot adjust based on what just happened. Every prompt starts from scratch. As soon as a task involves multiple steps, retries, or decisions-based outcomes, retrieval alone starts to feel stressed. The system can describe what should happen, but it can't move the process forward on its own. This is where agentic AI becomes necessary, not optional. Agentic systems are built around a loop instead of a single response. The system observes the current state, reasons about the next step, takes an action using tools, checks the result, and then continues. The output is no longer just text, it's a change in the environment. In the alert example, an agent doesn't stop after explaining the fix. It applies the configuration change, checks whether the alert clears, and retries or escalates it if it doesn't. The system now has awareness of before and after. That loop is the real difference. RAG answers the question of what information is relevant. Agents answer the question of what should happen next. This is also why agentic systems feel fundamentally different to work with. They can fail, recover, branch, and stop for the right reasons. They can store intermediate results. They can decide when they are done. Importantly, agents don't replace RAG. In real architectures, RAG is usually embedded inside an agent. The agent uses retrieval to gather context, but the decisions live outside the model's single response. The agent decides when to retrieve, what to retrieve, and what to do if the retrieved information is incomplete or conflicting. This combination is what enables systems to move beyond demos and into production workflows. So the real design question isn't whether RAG or agentic AI is better. The real question is whether the problem ends with an answer or continues with action. If the job is to respond, summarize, or explain, retrieval may be enough. But if the job involves acting, verifying, adapting, or recovering from failure, retrieval alone will eventually stall. That's when adding more prompts stops helping. RAG made language models usable by connecting them to real data. Agentic AI makes them usable in environments where decisions have consequences. One helps systems understand, the other helps systems move. And once you see that distinction clearly, it becomes much easier to design the right architecture instead of forcing retrieval to do a job it was never meant to do.